Let's take a look at the moment of inertia of a disk of thickness t rotating about an axis right there, and to give a visual. So if this is a disk here, and it's the moment of inertia of its rotating about an axis right there. A side view looking like that as the disk rotates about like that, or from a side view, I have my axis like this and it's rotating around like that. So I'm going to do it two ways. I'm going to do it what I call the hard way and then the easy way. So the hard way, dealing with calculus. So what I'm going to do is it's calculus, and I know the moment of inertia is the integral of r squared dm, and so I need to take some differential here and find the moment of inertia of that and then integrate. So I take a wedge right there, some distance r away from my axis of rotation. And if I look at this axis, or this triangle right here, that's what I have written here. This distance is big R minus little r, where big R is the radius. That distance from the center, this is the center, to that point on the edge is r, and so using Pythagorean theorem, we end up with that as the other side, which then, if I go ahead and square that binomial, and then combine, our squares cancel out, and I'm left with this. So this distance right here is that distance right there, and so the distance all the way across is twice that. My thickness is dr because that's my differential, and my thickness is t. So that becomes the differential of my volume of this little wedge right there. If I assume uniform density, rho is dm dv, where v is the volume, so that's big M over the total volume, which is m over pi r squared t. That's the volume of the disk, and that capital M is the mass as written on the previous page. So my d little m is equal to rho dv, which is my density times dv. And I know what dv is because I solved for that on the other page. And so I have now the mass, the differential of the mass of that thin little piece of the disk is equal to this. And so now I can take that value of dm, plug it into there, and I have a single variable at this point. So obviously that should make it easy to solve, right? I have 2m over pi r squared going from 0 to 2r, because r is the distance. Little r here is the distance from my axis to where my wedge is, and so the smallest distance is 0, and the largest is twice the radius of the disk. So I integrate from 0 to 2r of this. Factoring the square root of r out, I end up with that, which then gives me this constant up front times r to the 2.5 times the square root of that. So the question is, how do you actually solve that? And that requires looking it up. So, or trying to figure out how to solve it. So I let u equal the square root of r, which is r to the 1/2. So there's my du. In terms of dr, we end up with dr is equal to 2u du. This is going to allow us to get rid of our fractional exponent. So this is what we had before. Putting in the u substitution, we end up with that. And so now we have u to the 6th square root of 2r minus u squared du, going from 0 to square root of 2r. Now we're going to do the trig substitution, that u is equal to the square root of 2 big R sine theta. And so du is equal to that. Substitute in. We can now get rid of our square root there because I've got a 1 minus sine squared becomes a cosine theta. So I have this monster right there. Just make sure that as you're going through this, you're looking at the steps and can see how to do it. And it comes down to this. Because I've made let's back up for just a second here. So I'm now doing a trig substitution, and so I now have it in terms of theta. And it's my limits of integration now go from 0 to pi over 2. We now need to sort of distribute the exponents and combine like terms, and we end up with this allows us to get rid of that radical. And matter of fact, all of our partial exponents, all of our fractional exponents, gone. This is just from the previous step, combining the cosines. And now again, going through the simplification process. We need to somehow integrate that, so I want to get in terms of just one of the trig functions. I know cosine squared is 1 minus sine squared, so I make that substitution. I distribute, and so I end up with this integral of sine to the 6th power minus this integral from sine to the 8th power. I looked up, this is something I looked up, sine to the mth power theta d theta is equal to that. So if I look at sine to the 8th power, just plug it into this formula that I looked up. Don't feel like you have to reinvent the wheel in physics. The math's already been done for us. We have negative cosine theta sine to the 7th theta over 8 with those limits plus 7/8, again, just following the prescription there. And so I now have, whole thing is equal to 7/8 integral of sine to the 6th power d theta. Because that term right there ends up being 0 because you plug in pi over 2 into that. The cosine is equal to 0, plug in 0, the sine is equal to 0, so this whole thing is equal to 0, it drops out. And so this piece right here is just that, which means I now have a sine to the 6th and a 7/8 sine to the 6th, and so I can combine them into this. And so now it's simplified down to 8 over pi mr squared integral from 0 to pi over 2 of sine to the 6th theta d theta. So it's just a question of what is sine to the 6th theta d theta. What is the integral of that? And we use the exact same formula again. So we get it in terms of sine to the 4th. That's sine to the 4th. Again, this first term is going to be equal to 0. We plug into the same formula for sine to the 4th. We now have in terms of sine to the 2nd. And again, that first term goes to 0. And so now we're at sine squared. And it just works through piece by piece. And we end up with 5/4 times the total mass times the radius squared. Whew. That's a fun little time. Now let's do it the easy way. So I have a disk here, and I'm going to use the parallel axis theorem. So I'm going to look up at moments of inertia of a disk rotating about its central axis, and it's 1/4 mr squared. I'm now going to shift the axis from the middle to this point right here. So to shift the axis using the parallel axis theorem, we end up with the moment of inertia about the center of mass plus mr squared, because I moved the axis at distance r, and we end up with 5/4 mr squared. So I guess you're going to reinvent the wheel if you want to, but looking up, so much easier.